Hello biology students, and welcome to our second video where we're going to continue our discussion about water. So remember, to recap a little bit, in the last video we had talked about how water is a polar molecule. And this means that the electrons that are found in the covalent bonds between the oxygen atom and the hydrogen atom in our water, these electrons are not shared equally. They spend more time near the oxygen molecule, meaning the oxygen end of the water molecule has a slightly negative charge, and the hydrogen ends of the molecule have a slightly positive charge. Now this is important because if I have multiple water molecules that are near one another, my slightly negative, my slightly negative oxygen molecule is going to be attracted to a hydrogen atom on a different water molecule that is slightly positive, and this is going to result in that weak bond called a hydrogen bond forming, causing the water molecules to be attracted to one another. Now this idea that water can form hydrogen bonds allows water to have many properties that basically make it so life on Earth can exist. In fact, without hydrogen bonds, we wouldn't be alive. Hydrogen bonds are essential for life to be able to occur on Earth. So these properties, there's two big ones. So cohesion and adhesion are two biggies. Cohesion leads to a property called surface tension that we'll talk about later. Adhesion allows for a property called capillary action. And it also allows for some other properties like temperature moderation, density of water, and water being the solvent of life. So we're going to run through each of these properties in detail. So first, let's talk about cohesion. So by definition here, cohesion is an attraction between molecules of the same substance. So what we were just talking about, when I have one water molecule hydrogen bonding to a second water molecule, that is cohesion. Because we have two molecules of the same substance, two water molecules, that are being attracted towards one another via these hydrogen bonds. So this one we already kind of know, even though we didn't know it was called cohesion. Now, cohesion itself leads to another property that you might be familiar with, and that is surface tension. So I want to look at these pictures over here first. So first, I want you to notice that in this glass, the water in the glass seems to be filled up past the point where the glass ends. And this is called surface tension. Basically, all the water molecules in the water are bonding to each other via hydrogen bonds. And therefore, even if some of the water molecules, like the ones right here, are leaning over the edge of the glass, because they are attracted via hydrogen bonds to other water molecules in the glass, they don't spill over. Basically, they're being held on by other water molecules, allowing them to kind of look like they're suspended over the glass, even though they shouldn't be able to stay there. For another example, you can look at this picture down here. You can see you're actually able to float a paper clip on a cup of water, and this is because there are hydrogen bonds between the water molecules in this glass, and that is creating kind of a solid surface is the wrong word, but that attraction is creating a higher strength between water molecules, and that strength is higher than the strength coming from the force of gravity pulling the paperclip down. In other words, it's able to hold up the paperclip. So the way this works kind of on the molecular level, here I have a bubble of water, but kind of logic, water shouldn't be able to form a bubble on a surface, right? So water should lie down flat along the surface if you were to think logically. However, because each of these little water molecules that's represented by a circle, because they are each hydrogen bonding to the ones around them via these bonds right here, they're basically able to hold themselves up and create this bubble on the surface instead of lying flat. So that's due to surface tension, which is caused by cohesion. So a second very similar and important property is adhesion, and this is defined here as the attraction between molecules of two different substances. So if you had water hydrogen bonding to a non-water substance, that would be adhesion. So adhesion leads to something that we call capillary action. And capillary action is basically when water molecules hydrogen bond with another substance, and that this allows water to climb up that substance. So I'll give you a couple of examples. I want you to imagine if I had a little tube and the tube was put into a beaker of water. Now this water, the water molecules would form hydrogen bonds. If this tube were polar, they would form hydrogen bonds with the sides of this tube, allowing the water to stick to the sides of that tube. And maybe a water molecule that was right here would hydrogen bond a little higher up, essentially allowing the water to climb up the tube. Similarly, these water molecules that are climbing up the tube can also hydrogen bond to water molecules behind them, kind of pulling them up along as they go. So we have both the water molecules adhering with the side of the glass, but also cohering, having cohesion with the water molecules around behind them, kind of helping to pull them up too as well. So you might see this as when you look at a graduated cylinder. Remember, you've seen in previous science courses that the liquid forms a meniscus, and that is because water molecules on the side here are adhering, they're forming hydrogen bonds with the side of the graduated cylinder. Similarly, if you put a corner paper towel in a droplet of water, the water will climb up the paper towel because it is adhering or forming hydrogen bonds with polar molecules in the paper towel. So to kind of summarize, cohesion, looking at these cutesy little pictures, is two of the same substance bonding together. So I have two water molecules, where adhesion is the same idea, but it's two different polar substances. So water and something else, maybe glass, maybe paper towel. So water also has a lot of other cool properties that help life to exist on Earth. So first of all, water shows great temperature moderation. And basically what this means is that water can absorb a ton of energy in the form of heat and only change temperature slightly. So this is really important because if water changed temperature really easily, you can imagine on a sunny day, the temperature of the water in a pond would fluctuate wildly. It would get really, really hot. And then if we didn't have a lot of heat for a day or two, maybe it was really rainy or cloudy, the temperature of that water would get really, really cool quickly. So it's important that water can absorb a lot of heat and release a lot of heat, but not change temperature too much. Otherwise, all the living things in that pond would die. Similarly, we have a lot of water in our bodies, and if we were out in the sun, we wouldn't want our body temperature to go through the roof, rise really quickly, but fortunately that water in our body can absorb a lot of heat without changing temperature. Now, at first glance, this doesn't seem to have a lot to do with hydrogen bonds, but in reality, hydrogen bonds are essential for this process. So I want you to imagine, we already know from previous science classes that in liquid water, molecules are moving fairly quickly, right? However, in a gaseous water, in steam, molecules are moving much faster. So in a gaseous state, molecules are moving very fast, and in liquid, they're moving a little bit slower. So because they're moving a little bit slower in liquid, they have more time to form hydrogen bonds. So in liquid water, you see I have a bunch of water molecules that are hydrogen bonded to water molecules near them, where in gaseous water, molecules are moving so quickly and they're so spread out that these hydrogen bonds don't exist anymore. So this means if I want to evaporate water, or if I wanted to change temperature and go from a liquid to a gaseous state, one of the first things I would have to do would be to break these hydrogen bonds, because I can't have a gaseous state. Molecules can't be spread out unless these hydrogen bonds are broken. So therefore, in order to break these bonds, water has to absorb a lot of energy. It takes a lot of energy to absorb those bonds, which means that if you expose liquid water to an energy source like the sun, a ton of that energy goes into breaking the bonds instead of heating up the water, which means water absorbs a lot of energy and uses it to break the bonds instead of to increase the molecular speed, which is what heat is. So that's why it takes a lot of energy to actually heat up water. Okay. So a second kind of similar property is that water has a very unique property when it comes to its density. So in case, for those of you who don't remember, density is just a unit of mass per unit volume. So the more mass you have in a certain area, the more dense you are. So for almost all substances on our planet, the solid form of the substance is more dense than the liquid, because We know in most solids, the molecules are closer together than they are in the liquid form, making them more dense. However, water is unique. In water, ice is actually less dense than the liquid, which is why if you look at some ice in water, that's why the ice floats, because things that are less dense float over things that aren't dense. So this might not seem super important, but it's actually really, really important for living things. So first of all, if you think of a really cold climate where like maybe New England in winter or northern Canada for most of the year, there is ice on the surface of lakes. And this ice is actually pretty essential for the things that live in the lake because it acts as an insulation layer. It actually keeps the water down below warmer by not letting the heat escape. And this allows organisms that live in the lake to thrive and not die off in the winter. So it's pretty important. So again, it doesn't really seem like hydrogen bonds play a big role in this property, but again, they do. So let's look at how that works. So here I have that same picture from before, but now I've added in solid water. So in the gaseous state, molecules are moving so fast and they're so far apart that they are unable to form hydrogen bonds. In the liquid state, molecules are moving a little bit slower than in the gas, and because they're moving a little bit slower, they have time to form some hydrogen bonds with molecules near them. However, they don't form the full 4 bonds per molecule that the water has the potential to do because it's still moving a little bit too fast. However, we know in slow things that molecules move really slowly, right? In solid water, anything that's cold, the molecules move slower. So now, because the molecules are moving slower, they have time to form their maximum number of hydrogen bonds. You can see each water molecule is bonded to 4 water molecules near it. And it turns out hydrogen bonds are at a set distance apart. So whenever you have a hydrogen bond, those molecules are going to be at a set distance apart from one another. So this actually forces the water molecules to be a little bit further away from one another than they would be in their liquid form. You can see these 2 molecules that I've circled right here, they are further apart just by chance than these 2 that haven't formed a hydrogen bond. That hydrogen bond forced them apart. So by putting some forced in space here, this actually means that there is less mass per unit volume. So the solid actually has a lower density than the liquid of water, allowing ice to float. So finally, the last property we're going to talk about is the fact that water is the universal solvent. And what this means is basically water can dissolve tons of substances. Basically, it can dissolve anything that's ionic, and it can dissolve anything that's polar. And this is because water is polar. So we have this phrase called like dissolves like, which basically means that solvents, or liquids that dissolve other things, can dissolve things that are similar to them. So because water is polar, it can dissolve other things that are polar. Water can also dissolve a lot of things because it has a neutral pH, so it's neither an acid or a base, which is kind of a side note, but worth noting nonetheless. So let's look at an example of this. So in this picture right here, I have some salt. So salt is ionic, and the salt here is dissolving in water. So if we look at salt really closely, the chemical formula for salt is actually NaCl, with Na being the positive ions. You can see my little yellow guys are Na here, like here, here, here. And each of these are positively charged. They're Na+. And then each of my green ions, that's Cl-. So what happens when water dissolves salt? The negative end of the water, aka the oxygen molecule, is attracted to the positive ion. So I have my negative end of my water molecule being attracted to my positive sodium ion. So hold on, let me erase so I can show you this in a little bit more detail. So I'm going to zoom into this picture here. So I want you to imagine my Na+, that's a positive ion, and the negative ends of my water molecule, the oxygen, that slightly negative end, are attracted to the Na+, and they form what's called a sphere of hydration. Basically, they make a circle around the sodium ion, effectively separating it from the chloride ion. So they're basically breaking the salt down into its 2-ion form. Now the same thing happens with the chlorine. So you can see here's my chlorine ion, but you can see now all of the positive hydrogen ends of the water molecule, the little white circles, those are the ones that are facing in. The slightly positive hydrogens are attracted to this negative chlorine, again, effectively separating it from the sodium ion. So by separating the Na and the Cl, I'm allowing the salt to dissolve in water. Okay, so basically because water is polar, it can dissolve ionic things and it can dissolve other polar things. However, it cannot dissolve non-polar substances. So that's kind of its limitation. So it cannot dissolve things like oil, which is non-polar. So you might have noticed things like water and salad dressing don't mix because salad dressing is mainly oil-based. So when you have an Italian salad dressing that has some water in it and some oil, if you let that dressing sit for a while, the water and the oil don't mix. You have to shake it back up to get it to be more evenly distributed. So that's the properties of water, and I'll see you in the next video.